Hello, this is Dimal Shuaibi from Rochester Institute of Technology. In this presentation, I'll talk you through our work titled Learning to Characterize Performance Regression Introducing Code Changes. This work is a collaboration of 6 researchers from Rochester Institute of Technology, Prince Mohammed bin Fahd University, and University of Sfax. Now, let us go through the background and motivation of our work. Software development cycle had evolved in the last decade to cope with the development community needs into constantly pushing new features into the hands of their customers. To take an example, in continuous integration, continuous development pipeline, team members integrate their work frequently. Each integration is verified by an automated build and test to detect integration errors as quickly as possible in order to support development with the necessary feedback. A delay in any process should be avoided. As part of the testing process, several regression testing approaches were developed to accelerate the testing. So, to know more about regression testing, it makes sure that new modifications or code additions are not conflicting the existing software functionalities or specifications. More specifically, performance regression testing focused on finding degradation in the way the system behaves after running the same workload. In the example we have here, the commit colored by red includes code changes that are increasing the code execution time. Development team should be notified by this degradation after testing in order to resolve it. Testing in general became a complex and expensive process in CI systems. The code size and the number of developers working on the same system make reviewing code and finding errors troublesome. Many changes from different developers simultaneously might create bugs or changes that are degrading the system performance. As a result, there is a need for automated techniques to detect performance regression. Even with automated testing, challenges in the practice of performance regression detection still exist. Software testers find running benchmarks after each code change fastidious and might considerably delay the development process. Instead, they tend to run benchmarks periodically. Periodical performance testing might reduce testing costs, but it has its own challenges. First, it makes it difficult to fix. Periodical performance testing also gives rise to another problem, which is finding which code change within the tested time period introduces the regression. In cases where periodical tests captured regression, developers need to rewind all previous committed changes to debug and find which one is problematic. In addition, any performance enhancement followed by degradation will not be detected if the final performance time has not been significantly changed from the precedent testing results. In this situation, developers and testers are regularly trying to strike either optimally testing every code change for performance or increasing the productivity by ignoring performance testing or delaying it until the end of the development cycle. Limiting the search of finding regression became critical to save testing effort and time. Early analysis of code changes will help in identifying the patterns that might indicate potential performance regression. Code changes will be characterized based on information gathered from the early analysis. This approach will help by prioritizing the execution of performance tests only when the code is suspected to slow down the system. Though characterizing performance problematic code changes seem to be a good solution, it suffers from the lack of examples to learn from. The problematic commits percentage is only about 6%. This severe imbalance makes it difficult for the classifier to detect the minority problematic class. So, in this work, we will challenge existing resampling techniques to highlight their impact on the performance of performance regression detection models. The goal of this work is to formulate the identification of problematic commits introducing performance regression as a binary classification problem with balance detection for both classes. We aim to design and develop a model that is able to learn from history commits in order to flag any future commit showing regression symptoms as potentially problematic. The approach we adopted is divided into 3 phases. The first phase includes data collection and feature engineering. Second phase deals with the class imbalance problem and classifier model selection. Here, different models are trained and evaluated, and the one with the best performance for both classes is selected. The selected classifier model will be used in the third phase for the classification of any new commit. Developers will feed the classifier with static data from the recent code change they committed to reveal if any further performance testing is needed. We collect commits from a project repository that uses a version control system to find and generate set of features that describe those commits. We chose Git project because it is an open source and has a built-in performance tests. The goal of performance tests execution process is to identify commits introducing regression and also to collect data required in calculating dynamic metrics. The statistical analysis process is to determine the significant performance changes followed by the test execution. Dynamic and static analysis processes are to collect data required for metrics calculation. An example of those data are the list of reached methods by a test and also the number of method calls by a test. During metrics calculation, which is process 5, features are generated from the metrics difference between pair of consecutive commits to describe the latest one. The second phase starts with addressing the high class imbalance. Different sampling techniques have been applied and different classification models have been evaluated on the balanced dataset. The cross-validation process here is to split the dataset into training and testing. Only training dataset is sampled and that dataset is then used to train the classifier. Testing dataset is used to evaluate the trained classifier. The resampling techniques used in this work are random undersampling, random oversampling, and synthetic minority oversampling technique named SMOTE. Random undersampling is randomly deleting samples from the dataset to reduce the class representation difference. In a highly imbalanced datasets like the one we're working on, a big chunk of the dataset will be deleted, making the dataset too small. Random oversampling is randomly selecting samples from the minority classes and then duplicating them. In contrary to random undersampling, a random oversampling dataset size increases. SMOTE is another oversampling technique that adds new synthetic samples rather than duplicating existing ones. The new samples are created from the original samples belonging to the minority class. To select a model, we used different classification techniques to train and evaluate. prediction performance for both classes, the hit and dismiss classes, are compared. The best performance model is then selected to be used as the base model for phase number 3. The detection model is represented as a rule. The listing over here is an example of generated detection rule. We can see here that the representation can help developers better understand and analyze the performance of this classifier model because it is easy to read and easy to understand. The evaluation metrics used are recall, specificity, balanced classification rate, and geometric mean. Recall and specificity evaluate the detection of problematic hit class and the safe dismiss class respectively. By using recall and specificity, we will have a view on how a classifier is performing in detecting each class, but this does not help on choosing the best classifier. The two rates are conflicting in nature. As a result, we need to combine both rates so we can select the best classification model. Here we come to balanced classification rate and geometric mean. Those rates combines recall and specificity in order to evaluate the provided classifiers. The BCR, the balanced classifier rate, is the arithmetic mean of sensitivity, the recall, and the specificity. We included also the geometric mean because it measures the classifier improvement after the data sampling, and it also reflects the improvement of recall rate without greatly affecting the specificity. To evaluate our approach, we investigated the following research questions. In the first research question, we are interested in assessing the effectiveness of various resampling and classification techniques to identify the combination that is the best in identifying both commits classes. Answering the second research question is providing a look over proposed approach classification performance compared with other predictors. The experiments are conducted on the original dataset without sampling as a baseline to show the improvement of the resampling. As we can see, we have applied all resampling techniques on every classifier. The evaluation metrics, the metric values represented here, are the average of the 10 folds. To start with, SVM recall rates were 0 before resampling. The recall jumped from 0 to 0.7 after the random oversampling. This enhancement came along with a sharp reduction on specificity. This change is due to the fact that in SVM, the learned class boundary is strongly skewed to the major class, which result in higher false negatives. In this case, SVM will build models based on each class representation. This explains the recall increase with random oversampling as the same samples are duplicated, which directs SVM model during training to the major class after resampling. Bayes point classifier also not performing well with imbalanced dataset because it relies on the Bayesian approach that assigns weights to samples based on the posterior probability. As the training data is highly imbalanced, the classification based on the given weights will highly lean to the major class, which is dismiss class in our case. For decision forest, random oversampling shows a noticeable enhance on all performance metrics except true specificity. Specificity decreases because the dismiss class representation changed. Yet, random oversampling still provides the best detection of the non-problematic dismiss commits among the three techniques. Boosted decision trees models on a random oversampling dataset provide better results than decision forest in all metrics. Boosted decision tree classifier is balancing between the two classes, as the BCR value is showing. The geometric mean of boosted decision tree models with random oversampling dataset proves our finding that the recall improvement did not affect the specificity strongly as other models. For all classifiers, we can see that SMOTE did not provide competitive results. We anticipate that SMOTE new samples might add a little distraction to the classifier because the features values are calculated and not actually observed. Now we want to assess our predictor with other work predictors. Predictors included in the comparison are rule-based deterministic approach named Perfecy, KNN as a traditional machine learning algorithm, and NSGA2, which is an evolutionary machine learning algorithm. Boosted decision tree classifier on the imbalanced dataset was performing right below or same as the random classifier KNN in detecting the hit class. On the other hand, we can observe the huge improvement boosted decision tree provides on detecting hit class when trained by sampled random over sampling dataset. The recall improvement exceeds 50% in average. Evolutionary algorithm in NSGA2 provides highest average hit class detection due to the fact that solutions are picked to optimize recall and specificity equally without being biased to the mostly represented class. Decision tree with sample dataset did not provide a competitive result with NSGA2 in detecting the hit rate. The average of the recall of NSGA2 and our approach are 0.59 and 0.56 respectively. On the other hand, our approach provides much higher specificity than NSGA2, where the average specificity of NSGA2 is 0.6 and 0.85 for our approach, along with only 3% difference in the recall. Boosted decision tree with random oversampling is also the best balancing due to the improvement of hit class detection that is not aggressively declining the detection of dismissed class as in NSGA2. The nature of the research problem requires solution providing high detection of commits introducing performance regression. At the same time, solutions should not be expensive. Increasing recall and decreasing false negative rate leads to less testing and cheaper solutions. Many solutions are providing high recall without considering false negative rates, which leads to conducting unnecessary testing on stable commits. To conclude, we found that machine learning models were more sensitive to performance regression imbalance data. They were an enhance in predicting minor class but did not outperform genetic programming approach. In general, we recommend software engineers to first understand dataset type and then decide what action performed on it for cleaning without changing data properties in a way that might manipulate and control results. Second, we recommend software engineers to pick evaluation metrics based on the problem nature they work on. In this contest, we are interested on predicting code changes introducing performance regression that leads to the choose of recall and specificity rates. We found those metrics giving the accurate performance of classification approaches. Thank you all for listening to the talk. I will be happy to answer your questions.